This is Physics Lab 3, Black Hole by Catherine St. Jean. So here's a quick introduction to the lab. The purpose was to determine the mass of a black hole through an orbiting star, and then determining what speed a spaceship must go to avoid crashing in the system of the black hole. Some models and principles that we used momentum, parallel and perpendicular forces, universal gravitation, and Newton's second law. Preview of results. So black holes are quite massive, but we can determine the mass using using universal gravitation and physics, and faster speeds are necessary to escape massive gravitational forces. So the experiment was in two parts. In part one, the system is a star and a black hole. We must determine the mass of the black hole using our fundamental principles in GlowScript. In part two, you have a spaceship approaching the same black hole and a planet orbiting the same black hole. So the system is the planet, spaceship, and the black hole. We want to get off of the planet and fly around the black hole and then leave the system. So we had to determine this in GlowScript as well. So here are the fundamental principles that we used. First, we have Fnet equals F perpendicular plus F parallel. We have the momentum principle. We have universal gravitation, and we have the position and velocity update formulas, which use Newton's second law. So first, we use the momentum principle in part one of my coding. In lines 166 and 169, I applied the momentum principle, and then I broke it into parallel and perpendicular components in lines 174 through 183. And then to find the mass of the black hole, I rearranged the universal gravitation formula to isolate the mass of the black hole. Here are my part one results. This is my mass of the black hole. It's approximately 1.3995 times 10 to the 34 kilograms, but this is a source of error because the coding spit out the value of the mass at different points in the orbit, so I had to average it. So this mass is an average. And here's my Fnet, my Fnet parallel, and my Fnet perpendicular components. So here is part two of the coding. In lines 80, 83, 94, and 97, you can see that I use the universal gravitation formula. And once I have all these forces of gravity affecting one another, I found Fnet on the planet and Fnet on the ship. And once I have these, I can now use the position and velocity update down in lines 105 through 109 to find the updated velocity and position of both the ship and the planet at every given time. And once I have these, I kind of used a guess and check method of trying different speeds in the X and Y to see if the ship could safely leave the orbit without crashing into the planet. So here we have my results for part two and the initial velocity needed to leave the system and not hit the planet or the black hole. A source of error in this method is that it was guess and check of determining velocity. So it also should be noted that the speed of light is 3 times 10 to the 8th, and the ship is going slower than the speed of light because nothing is faster than the speed of light. Down here in the diagram, the magenta line is the ship's path, and the cyan line is the planet orbiting the black hole. So what does it mean? In part one, we assumed that the net forces, parallel and perpendicular components were the same as the rate of change of momentum. But the difference between these is that the rate of change of momentum is at a specific instance, while net force is the sum of all forces. In another scenario, with more forces at play than just gravity, Fnet would include other types of forces. What if? So here we have the initial velocity needed for the spaceship to actually enter a circular orbit around the black hole instead of leaving the system. So notice that the y speed is exactly the same as my previous one needed to leave, but the X speed is slower. The X component is slower.